in various ways, including simpler in the technical sense of Lie group theory. It's called a simple Lie group. And then those two groups are non-compact if you think of them as manifolds, but these other two are compact. So the unitary group consists of all n by n unitary matrices, and it's compact. And then the special unitary group, that's the intersection of SLNC and UN. So that's the unitary matrices that have determinant 1. So those are all classical groups. There are other groups considered classical. I said that classical is a somewhat fuzzy concept. A group is classical if it's a group acting as linear transformations on a vector space that preserves some kind of nice geometrical structure. But what's nice? Well, some things are more nice than others. But you'd have to say that these guys here are the Bach, the Haydn, the Mozart, and the Beethoven of classical groups. And just like classical composers, there are other composers deemed classical. But I think everyone would agree that those are classical. Well, actually, if you know too much about music theory, you might not call Bach a classical composer. Actually, he was Baroque. But underlying all of these is a fellow that's not a group at all. It's the monoid of all n by n complex matrices, or if you like, all in transformations of a n-dimensional complex vector space. I see my cases don't match here. And so that's not a group, but it turns out that that should be included in this family because in some sense it's the most fundamental of all. So I would probably call it the Palestrina of classical groups, because Palestrina is definitely not a classical composer, but all of classical music theory is sort of grows out of Palestrina, you might say. So I'll actually focus a lot of attention on that. So we're going to look at how to get representations, irreducible representations of these various entities. I just want to mention for the whole Zoom audience to hear that I'm cranking out more lecture notes. And so you can get lecture notes on Young diagrams, but now also on my next topic, thinking diagrams, at that URL there. Okay, so let me state a theorem along the lines I'm talking about. So it says that the algebraic irreducible representations. So I will define what that adjective algebraic means. Of the full linear monoid, n of Cn, are classified. Well, they're classified by Young diagrams. Again, we don't care too much about the difference between isomorphic representations. So when I say classified, I really mean up to isomorphism. And by Young diagrams, but not all Young diagrams. That would obviously be fishy because that would not depend on n. Well, it might be true, but it's not anyway. Young diagrams with less than or equal to n rows. So there's one algebraic irrep for each of those Young diagrams, and that's all of them. So what's this algebraic business? So let me explain that. So remember, a representation of this full linear monoid. What is it? Well, it's a monoid homomorphism. Any representation of any monoid is a kind of monoid homomorphism. And it's a monoid homomorphism going from your monoid, which in our case is this full linear monoid, to the linear transformations on some vector space. But you'll notice that looks suspiciously similar in this particular case, but it doesn't need to be the same vector space. So, well, I could use some other finite dimensional vector space, but they're all isomorphic to C to the n. So there's no loss of generality in saying what I said. And okay, so that's what a representation is. What does it mean for it to be algebraic? Well, this is a process here that you take a matrix and you get a new different size matrix. The new matrix entries here will be functions of the old matrix entries here. And we say the representation is algebraic if the new matrix entries are polynomials in the old matrix entries. Or so you could say a little bit more spiffily. So it's algebraic if the matrix entries of row of X, where X is any diagonal full linear monoid, are, let me say it this way, algebraic functions of the matrix entries of X. This is, in this particular case, when we're talking about this full linear monoid, this is just like a somewhat show-offy way to say polynomials. We could consider other monoids and groups, and indeed these other classical groups here. And then for each one of these, we could talk about algebraic functions on the groups, which might sometimes depend on the matrix entries and their inverses. Or polynomials, sorry, they might be polynomials and inverses of polynomials. But in this particular case, no inverses of polynomials need apply. So we could just say polynomials if we wanted to. So why do I want to consider restricting to these algebraic irreps? Well, the problem is that if we don't, there are just way too many irreps. And the project of classifying them becomes a very different kind of project. So let me just show you. So for example, suppose alpha is an automorphism of the complex numbers. And let's say not the identity. So a field automorphism. So the one that leaps to mind is complex conjugation. So then we can do this trick here. We can get a representation of the n by n complex matrices as follows. It'll be a representation on CPM, actually. So it will just be a homomorphism of monoids from these matrices to themselves. But what will it be? We'll just apply alpha to each matrix entry. So if you apply a field automorphism to each matrix entry, that clearly gets along with addition and multiplication. So it gets along with matrix multiplications. So it preserves matrix multiplication. So this will be a monoid homomorphism. So this will be a representation of your full linear monoid, but it's not algebraic because things like complex conjugation, they aren't polynomials. So this is a representation. In fact, you can check that it's an irrep, irreducible representation that's not algebraic. Now, although I only mentioned complex conjugation, there are zillions of automorphisms of the complex numbers. The Galois group of the complex numbers is an enormous, absurd thing. And so, while it could be interesting for some purposes, we don't want to get into that here. So we don't want to think about all these tricks. So we just want to stick with ways of building up representations that are, we can write them down using nice formulas involving polynomials. And then it turns out that your Fs are classified by Young diagrams. Okay, so how does it work? How do you actually get all these algebraic Fs using Young diagrams? Well, it turns out it's a very general method that works not just for this one theorem here, but it actually works in various slightly different ways for all these classical groups and even other groups. So it's a very good thing to think about in general. So let me say it in general. What's the trick? And it's an amazing trick which really reveals the true significance of Young diagrams. So here's the deal. So suppose M is any monoid. And let rep of M be its category of representations. And well, if you're interested in algebraic representations, then we could mean that that would only make sense if M was an algebraic monoid. But don't worry about that so much. So the real point is that I told you a little bit about how you can talk about representations, and then we can talk about morphisms between representations, and they form a category. So that's what I mean by rep M. And then any Young diagram, it's called Y, knows how to act on this category. So what it does is it gives a functor, which I'll call Y tilde, from rep M to itself. And this is called, it has a name, this is called a Schur functor. I'm sure that Schur didn't know what functors were, but he was involved in this stuff. So now I don't want to scare you. You shouldn't be scared of categories. They're actually very friendly, but some people might find this a little scary. But the main thing I'm going to do with this is something extremely simple. So a functor, what it does, right, is it sends objects to objects, sends morphisms to morphisms, in such a way that composition of morphisms is preserved. But all I'm going to do with it is use the fact that it sends objects to objects. So what I'm going to do is say, hey, you give me a Young diagram, and then I take any representation of any monoid in the world, I can get a new representation of that monoid. So a Young diagram is a trick, a method for getting new representations from old ones. And that's why representations are so often classified by Young diagrams, because we'll see that very often a group or a monoid will have one obvious representation that's just screaming out to be thought of. And if you take that obvious one, then you hit it with these Schur functors and you get lots of other representations. And in nice cases, you get all the irreducible representations of your monoid by that trick. And so if you want to think about a puzzle, you may try to think about what's the obvious representation of this monoid here. So that's the one that we're going to hit with our Schur functors to get all the algebraic irreducible representations of the full linear monoid. So let me tell you how this trick works. And I'm not going to prove this thing is a functor. I'm just going to tell you what it does to an object. So I'm going to tell you how to get a new representation from an old one and a Young diagram. So first of all, I have to tell you some more simple-minded trick for getting new representations from old ones. So suppose I have two different representations of a monoid. So let's say I have a representation rho of some monoid where it's a representation on some vector space V and a representation rho prime from that monoid on some vector space V prime. So I may have already mentioned that you can form, I have already mentioned that you can form the direct sum of these two representations, but there's another basic trick called the tensor product. So that will be a representation of your monoid on the tensor product of your two vector spaces V and V prime. And it works in the same kind of way as the direct sum does, in a general sense. So each monoid element is supposed to be turned into a linear transformation of this vector space V tensor V prime. And so we just do the most simple-minded way of doing that. So rho of M is a linear transformation of V. Rho prime of M is a linear transformation of V prime, and you can tensor linear transformations to get a linear transformation on the tensor product of vector spaces. So it's just one of these sort of off a log easy type ideas. Okay, so that's if you have two. But the game was supposed to be that if you just give me one representation of a monoid, that somehow we can hit it with the Young diagram and get a new representation. So why am I talking about two representations when I'm supposed to be just starting with one? Well, there is a way to get two things when you have one, which is that you use the same one thing twice. So what you can do is you can take a representation and just take its tensor product with itself. And you can do that any number of times. So let's start there. So given just a single representation, say rho of our monoid on some vector space, we get a representation called rho tensor with itself n times, and it's just the tensor power of rho. We just tensor with itself n times. Tensor product is associative up to isomorphism, so I don't really need to worry about the parentheses here too much. And this will be a representation on the vector space that's just V tensored with itself n times. So that's an easy way to get a new representation from our original one here, rho. And that's the basic trick. But it turns out that if you start out with an irreducible representation of a monoid and you form a new representation this way, usually that new one won't be irreducible anymore. Sometimes it will, but usually it won't. And so we have to get more creative than just this if we want to actually get a whole bunch of irreducible representations of, for example, the full linear monoid, starting from just one. And that's where the Young diagrams come in. Because remember, we've seen that Young diagrams describe representations of the permutation group or the symmetric group. And the symmetric group comes into this game here Because when you have n copies of V line up next to each other, one thing you can do is you can start doing permutations on the factors here. And so that's where the Young diagrams really come in. So sorry, I think I'm going to get very sorry. I should never have called two different important concepts n, but I've been trying to use lowercase n for the number of boxes in a Young diagram, and that's consistent with what I'm doing here. And I want to use capital N for the number. Let's see. I want to use capital N sometimes for, yeah, like when I say GLN or the endomorphisms of CN, that's a different thing, a capital N. Okay. Obviously, I'm not doing too well here. Should have used a different letter, but okay. So, but also Sn, and thus the group algebra of Sn has a representation, which I'll just call R, on the same vector space. So how does that work? So I'll tell you how it works for a particular permutation. And it just does the obvious thing. Remember, every vector in this tensor product of vectors, this nth tensor power of V, is a linear combination of vectors that are written like this. They're just written as tensor products of vectors in the vector space V, so an n-fold tensor product like that. And what R of sigma does is it just permutes those guys. Now, it turns out that if you want to get a representation, you have to be a little sneaky. You need to use the inverse of sigma. There's some general rule that whenever you have a letter to the left of a letter, and then later on you put it over to the right, that you're in trouble, and you're punished by needing to like stick in an inverse, because an inverse switches the order of things. So that inverse in there. So you can check that this is a representation. And so this is how it's defined on these vectors that are tensor products, but then you extend by linearity to all of this vector space. Also, these group elements are just some of the elements in this algebra here, but everything in this group algebra is just a linear combination of these sigmas. So once we know how these sigmas act, we define how the whole group algebra acts, again, by extending by linearity to make R sigma for other things be linear in that argument. So you do it like this, and then we just say extending by linearity. So now so that's a thing we can do. So now here's why this actually does what we want, namely give us a recipe to get a new representation of M from our original one here, rho. So what we have is, right, two different representations on the same vector space. We've got one, rho tensor n, it's a representation of our monoid M, but then we've got another, capital R, which is a representation of this group algebra here. And the interesting thing is that they get along well with each other. For some reason, I like writing on these upper boards better. The lower ones are so dark. It seems sort of cave-like down there. So here's the relationship between the two representations that I've just described. they commute. So in other words, I could do like R of anything in the group algebra, but I could also do this representation rho tensor to the n for anything in my monoid. And so both of those are linear transformations of the same vector space, V tensor to the n. So we can ask if they commute with each other. And in fact, they do. So this is the cool part. And if you can just do a calculation and easily see it, but I want you to understand that it's like a really fundamental idea. So it's sort of like, imagine like this, you have like suppose you're like a chef doing some show off thing where you're like cooking n different omelets. So then there are things you could do. You could like permute the omelets. You could go and go switch, or you could do the same thing to every omelet, which is what we're doing here, right? We're applying rho of m to each omelet. So you could like throw some red pepper on each omelet. So what I'm saying here is I'm saying that if you throw red pepper on every omelet and then you permute them, it's the same as if you permute them and throw red pepper on all of them. So that's just the basic idea behind it. And so what that means is that the operations coming from the symmetric group and its group algebra get along very nicely with this representation we have. And so that lets us build new representations from it. So remember, now let's bring on our Young diagram. Any Young diagram with n boxes gives an idempotent. Let me call this Young diagram Y. It gives an idempotent in the group algebra. It gives a minimal idempotent. We don't really care quite as much about it being minimal right this second, but it's actually also important. So let's call it pi sub y. So remember, that was a guy in the group algebra that squares to itself. That's what idempotent means. So what that means is that if we apply any representation of the group algebra, like this one R, that will be an idempotent, right? Because if you square that, because it's a representation, it's just R of pi y squared, so it's just R of pi y. So that guy is an idempotent too. And what it is, remember, is it's a linear operator from V tensor itself n times to itself. So it's an idempotent operator on V tensor itself n times. Now, what you should always want to do when you have idempotent operators is do things like look at their kernel, which is all the stuff killed by it, but also look at their range, which is all the stuff not killed by it. And of course, because it's idempotent, everything in the range, when you hit it with the idempotent again, it doesn't get changed again. So it's a way of cracking a vector space into two parts. That's what idempotents are good for. The kernel
Question.
Yep.
I was with you here with the inverses,
Yep.
but then when you made it an element of the group algebra, how do you invert it?
You don't invert anything in the group algebra.
Yeah, but I mean, you're talking about group algebra.
So if I take a linear combination of sigmas, like say I had like sigma 1 plus sigma 2, and I wanted to know how to do R of that. Then I would do sigma 1, and I'd write this thing down, and I'd do sigma 2, and I'd write the similar thing down, and then I'd add those. So the addition is not supposed to slip into the inversion. Yeah, so yeah, that would be bad, because not everything in the group algebra is invertible. So this is just for the, remember, the group elements are a basis of the group algebra. And so once you know what you've done to a basis of a vector space, then there's always like a way to linearly sort of extrapolate it to the whole vector space. And that's what we're doing. Yeah, thanks. So, okay, so we get this idempotent here. And then we get a vector space, which is the range of that idempotent. So I don't have a great name for it. Actually, I do. I'll call it y tilde of v. I'm overloading the term y tilde a bit, but I think it's good. Let y tilde of v be the range of this idempotent. So it's some subspace of our big vector space here. And so what I'm claiming is that now we get a representation of our monoid on this subspace just by using the fact that we already had a representation of M on this larger space. So we get a rep y tilde of rho on this vector space y tilde of v by y tilde of rho applied to any monoid element. It's just we use our original, we use the representation we already had on this larger space. And we just restrict it to this smaller space. But the key point is that this operator here maps this smaller space to itself because of this commutativity formula. So you see, if we had a vector that was in the, so like let A be this idempotent here. So if we had a vector in the range of that, so we take a vector and hit it with R of that idempotent, we get a vector in the range of that, and then we act on it, we get something else, which is again in the range of the same thing, because here's the formula saying it's R of A applied to that thing. So thanks to this wonderful commutativity property, this this operator here maps this subspace, the range of our idempotent, to itself, which is the most basic thing you need in a representation, is that any monoid element is supposed to get turned into a transformation of some space that maps that space to itself. Did I screw up? That's bizarre. Okay. How can it turn into a V as soon as you pointed to it? Huh? He's just showing off his powers. So yeah. So yeah. And it's a represent and you can check that it's a representation. Check that y tilde obeys the rule of being a representation. You know, the y tilde of the product of the two monoid elements is the y tilde of one times the y tilde of the other. Check that. I think all you need to use is this thing again. So that's the idea. So the idea is that you start with a representation, you tensor it with itself a bunch of times, you get something huge, and then you bust it into pieces using Young diagrams, or each idempotent coming from your Young diagram knows how to project that big space down onto a piece. And you get representations that way. So that's a super general trick. Then when you apply that general trick, you have to do more work to see what these new representations are like. But they're always interesting. But depending on the monoid you started with and the representation of it that you started with, different things will happen. And so I'll do it to this full linear monoid. So now let the monoid that we're thinking about be the one that I really want to look at, all the linear transformations of C to the N. Notice that's a different font N there. Should be, yes. It's unrelated to this lowercase n here, basically. Okay, so what? So we got to start with a representation of this. So this has a representation. It's indeed, in fact, an algebraic representation, if you want to know. And in fact, well, okay, that's good. It's an algebraic representation. What is it? It's so obvious, it should be called the blitheringly obvious representation, but people sometimes call it the tautologous representation, or maybe sometimes they call it the fundamental representation. All of these are words that are designed to make you feel embarrassed for asking what representation I'm thinking about. Right? Various fancy words to mean, come on, you know what I'm going to do. So what is it? So a representation of this monoid, or any monoid, is a homomorphism to endomorphisms of some vector space. Well, duh. So we're going to use this exact same vector space, and we're going to use the identity here. So that's the tautologous representation. I'll still call it rho, because it's playing the role of our rho here, but it's just the identity map. Okay, so starting from that one, then we build more using Young diagrams. And potentially we could use Young diagrams of any shape or size. But the theorem goes like this, that if Y is a Young diagram with less than or equal to n rows, then you can do Y tilde of this tautologous representation, and you get an algebraic irrep of this full linear monoid, end of Cn, and even better, that we get all of them this way. All the algebraic ones this way. When I say all, I mean, of course, up to isomorphism. So we say that, so that's why the irreps of the full linear monoid, or at least the algebraic ones, are classified by these Young diagrams. Yep.
So, not to be that person, but if you ask me what the obvious representation of GLN is, then I either say it's that one, not representation, or I say it's the trivial representation.
Okay, well,
But you can't do, I guess there's
well, you could,
trivial representation. I mean, you can't make every element of the full endomorphisms act as the identity, because I mean.
you actually can, because we're just demanding that it's a, so it does have a trivial representation. Every monoid has a representation where all the monoid elements act as the identity. Yeah, Yeah, if you're talking about algebra representations, then that
Okay.
zero would have to go to zero, not
And then
one.
that's-
But we're not like talking about algebra
And
representation.
that's what corresponds to the empty Young diagram.
Yeah, that's right. So the point is, yes, every monoid does have that trivial representation. So if I just gave you, if I just said, I have a monoid in the box, what's its obvious representation? That's all you knew, then the trivial representation, which should be the one you pick, because you can't really think of much else. But the point is that when you start tensoring the trivial representation with itself a bunch of times, you still just get the trivial representation, and any sub-representation of it's either going to be zero or one-dimensional. So you're never going to get anything fun out of that. So maybe I should say like the most obvious yet still entertaining representation or something like that. Yeah.
A question from Zoomland.
Yes.
Is the correspondence between Young diagrams and irreps of NCN bijective, or is it just a surjective map that generates every algebraic irrep?
It's bijective. Oh, I didn't say it right here. I said it earlier. Yeah, okay, thanks. I didn't say it in a strong enough way. So let's say, yeah, let me say it right. So we get a bijection between such Young diagrams, ones with the most n rows, and algebraic irreps up to isomorphism. Thanks. Yeah, it's really important that it's like so neat. For a bunch of the other classical groups, we get theorems that are similar to this, but they're like they have a little bit more fine print. Like sometimes we don't get all the irreps, but we get all of them except for some others that you can easily describe. But this is quite neat. Let me just say a little bit about this. I'm not going to attempt to prove this at all. It really does rely heavily on the fact that Young diagrams give minimal idempotence. That's sort of what's giving the irreducible representation. It's also relying on a thing that I don't want to get into too much, called oh boy, not at all. Called Schur-Weil duality. But I see the time is rushing by. Yes? Is that a question?
No.
No, okay. So I will not expound on that anymore. I'll just spend a couple minutes saying a little bit about, I gotta say a little bit about why at most n rows. So if you look at a Young diagram that has a whole bunch of rows, well, the easiest one to look at is the tall, skinny Young diagram, or a tall, skinny Young diagram. So if you take a Young diagram like this, and if we say that it has like m rows, if we take that y, if we apply that, remember, part of building this representation is applying this y tilde thing to the vector space. That's how we get the vector space for our representation. So if we apply that here, then this thing is called the exterior algebra, or the exterior, it's part of the exterior algebra. So what this thing is it's the completely anti-symmetric tensor. So it's a subspace of it's a subspace. Sorry, I know what I'm doing wrong here. Let's see. Yeah, probably I would be. I'm mixing up my. Yeah, no, that's all fine. So, yeah, so it's a subspace of the m-fold tensor product of this vector space with itself. That's by how we set it up. But which one is it? Well, it's the one consisting of what are called completely anti-symmetric tensors. So what that means is that it's a subspace of this thing consisting of tensors such that when you apply any permutation, like any elementary transposition to it, that you get minus what you had before. So I guess what I'm saying is that when we do rho when we apply this representation of the permutation group to a vector in here, it just changes by multiplying by the sign. So if you know about completely anti-symmetric tensors or exterior algebras or Grossman algebras or whatever you want to call them, there are many different names for the same thing. You'll know that when M gets to be above N, there's just a zero-dimensional space of such things. So this representation we're getting here becomes zero-dimensional when M exceeds N. Now, if you look back very carefully at my definition of irreducible representation, if you'd been like very careful, you would have said, hey, you're saying that the zero-dimensional representation is irreducible, because I said representation is irreducible if it contains no sub-representation except the zero-dimensional one and the whole thing. But in this particular case of a zero-dimensional representation, the zero-dimensional representation is the whole thing. So you could say, okay, look, you're even getting an irreducible representation now, but it just happens to be a zero-dimensional one. However, by fiat, we declare that we don't count zero-dimensional representations as irreps. So this is like a new rule that I'm imposing. We won't call zero-dimensional representations irreps. And you may have encountered the exact same thing earlier in your life when somebody informed you that 1 is not a prime number, even though it seemed to be obeying some definition of prime number. Why did we decide that 1 is not a prime number? It's not because we just don't like it. It's because we want unique prime factorization. And if 1 is a prime number, then you can stick as many 1s in there as you want. Similarly, we want to be able to say, at least when it's true, that you can decompose a representation sort of more or less uniquely into irreducible representations. And if you allow zero-dimensional ones, you could add wads of those. So we will rule that guy out, okay? And so then we see that when our Young diagram looks like this, as soon as it breaks this rule here, we're not getting an irrep for the simple reason that we're getting a zero-dimensional representation. Now, that's just a special case of the situation we have any old Young diagram that breaks this rule. But it turns out that that's sort of always what's going on. If you have a Young diagram with more than n rows, you get a zero-dimensional rep from it. So in general, Y with more than n rows will give a zero irrep or zero-dimensional rep. Of this algebra of n by n matrices. So that's why we get that cutoff there. And if you look at the other, so in my lecture notes that I put on my website, if you look at the other classical groups, you see that they always have similar theorems like this, where there's some kind of cutoff, which could be n, or like for SLN, see the special linear group, it's n minus 1. And then sometimes something really weird happens right at n. But this is like the cleanest case. So I'll quit with this one. And I'll just say that, so what's really going on here is that the reason why Young diagrams know how to act on the category of representations of any monoid is because the categories of representations of monoids are especially nice categories. They're categories that I call two rigs, meaning that they have a kind of addition, direct sum, and they have a kind of tensor product that's a whole lot like a ring, but without negatives. You can't subtract representation. So it's like more like a rig, but it's not just a set, it's a category. So we glorify and say it's a two rig. And then it turns out that the free two rig on one generator, using this definition of two rig that I haven't quite given you, is a category where the irreducible objects, the ones that you can't chop apart using direct sums, are Young diagrams. So the Young diagrams are the irreducible objects in the free two rig on one generator. And so that's like the more slick way to say what's so great about Young diagrams. And so what that means is that if I have any two rig, like the representations of any monoid, and here's my free two rig on one generator, if I pick out where that generator should get sent, well, it gets sent to say some representation of a monoid. That determines a functor uniquely. And so now any Young diagram gets sent to some representation. So what we've seen is that a Young diagram plus a representation of any monoid gives you another representation of a monoid. And so what I did is I described the concrete way of how you get that to work. But with Joe Moeller and Todd Trimble, we wrote a paper where we proved that there's this free two rig on one generator where the irreducible objects are the Young diagrams. And that's sort of lifting this whole story up to a slightly higher level of abstraction and letting you see the Young diagrams as objects, as things in themselves, not just pictures. Okay, so I'll quit here and we can have questions then. Still some time. Any questions from the non-Zoom audience?
Are you going to be in the common room again?
I'll be in the common room as well. Yeah. Are there any questions from the Zoom audience?
Thank you. Just wow.
Okay, that's not a question. Jules?
Okay, so I guess part of what you're saying is, if you know the representation theory of the gamma true, you can kind of stop by treating geometric and reversible and study the monoid piece, or square matrices and representation theory survives intact.
It survives intact and it gets a little bit better. When you go down to the invertible matrices, then you get an extra kind of representation that you didn't have in this story here. Namely, you can take the determinant of a guy in GLN and take its inverse, and that the inverse of the determinant gives you a new representation of GLN C that wasn't one of the ones I talked about here. It does not come from a Young diagram. So because you've said the determinant is invertible, you get this new representation. And so the story for GLNC, you just made me say it, is that you classify the representations by Young diagrams with less than n rows together with an integer. And the integer tells you the power of the determinant representation that you want to use. And since n row, tall, skinny diagram actually gives you the determinant representation, you don't need to go up to n rows, you go up to n-1. So it's a somewhat more fussy story because you're letting yourself take advantage of the fact that the determinant's invertible there. Yeah. But this is like the clean story. So I should thank my friend Alan Knudsen when I said, like, oh, I'm going to tell him about Young diagrams. I'm going to say blah, 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 like all the usual stuff that everyone says. And he said, no, don't do that. Tell them about this. And then I realized, of course, because I've been doing this super abstract stuff with the Young diagrams, and the abstract stuff fits together better with this story. But I somehow never realized that, like, hey, you don't need fancy schmancy category theory to say this. It's just easier than talking about the groups.
I didn't get to my question. That was just backup.
Oh no.
We should actually stop there because it's 4 o'clock. We should quit the room, but we can carry on in the common room, right?
Okay, I'm sorry. We got to go.
Yeah. Okay. Thanks, John.
We wanted to get it done.